Um, let's see if we can build a joint probability distribution. So I gave you one based on the book, but let's try to build one ourselves. Let me share my Excel sheet. I would like to build a joint probability distribution with the two classical examples of flipping a coin and rolling a die. So what I want to do is I want to say, what if you flip a coin and roll one die? So that one variable is the coin flip, the other variable is the die roll, and what is the probability of your combined outcomes? So let's see if we can try to build one ourselves. Let's say that flipping my coin is my x variable. So I'm going to say here that x is flipping a coin. So my outcome would be heads or tails. And let's say that y is rolling my die. So my outcome can be 1, 2, 3, 4, 5, 6. Let me just write them down. My outcomes for y are 1, 2, 3, 4, 5, 6. My outcomes for x are heads and tails. And you can write this down while I try to make it a little bit prettier here. Is anybody here a musician? Am I really in a class with no musicians?
I'll listen.
I used to play violin until high school.
You used to play violin until high school.
Yeah.
What happened?
Violin's tough.
Did you get bullied into letting it go?
No, I chose sports over playing the violin in college.
You chose what?
Volleyball.
Okay, nice.
I chose soccer. Football. All right. Let me just make this a little nicer. Well, that's unfortunate. I was thinking if there wasn't a musician in the room, I did bump into an interesting way of comparing discrete and continuous sample spaces, and it's with fretless and fretted instruments. So I play a lot of string instruments, mostly guitar, but also bass. And you know, the basses I have are fretted. They have frets, which means that you can really only play every half note. That's it. There's nothing in between. I increase the tension and decrease the tension, right? But there's also fretless basses, and with fretless basses, you can actually play any note on the spectrum of your string, and that's pretty interesting because with a fretless bass, essentially the options that you have are continuous. You have an infinite number of options of notes to play. With a fretted bass, your options are discrete. You have a finite number that you can actually count. And I said, wait a minute, that's a really nice explanation if I was teaching to a class of musicians, like statistics for musicians or something like that. But this is statistics for engineers, so we got to think of boring things like tools in a manufacturing thing or something. You can put together this table. I'd like to know what those probabilities would be like. Any ideas? Like if I say, what's the probability that I landed on head and 3? If I, what?
50%.
50%?
Or you said and 3?
And 3.
Yeah, never mind.
Not 50%? Okay. So
30.
is there any way to figure out how we can find the probability? Or any probability here?
So for the x value, it's 50-50 the whole way down.
Okay, so we know at least what's going to be if we add them up, right?
Yeah.
So even though we may not know exactly the values in between, we know that if we were to add them up, we would get 50 for heads and 50% for tails. Is that correct?
Yeah.
Good. And this would really be my joint probability distribution for F. For X. All right. We know this much. What about for Y? What will be the marginal probability for Y? maybe we don't know the values in between, but if we can add them up.
1 and 6.
1 and 6? Yeah, that's correct. And in the chat, somebody also said 1 and 6. That's correct. Thank you, Christian. Wrong sheet. Here we go. So we know this would be over 6. And this would be the marginal probability of 1. Good. How do we know the probabilities of each individual combination of points?
Did you multiply them together?
Would you multiply them together? Is that what you're saying?
Yeah, like 0.55, 0.167.
Okay, so you're saying we can multiply them together, so 0.5 times, and I'm going to fix the row here. So 0.5 times 0.167, and I'm going to fix the column here. So we get that the probability here is 0.083, okay, for any one value. Now, it's an interesting thing, both the die and the coin are pretty much uniform, right? Every single value within their own, within those variables has the same probability. Can we expect the joint probability to also be uniform if my individual marginal probabilities are uniform?
Yes.
Okay, so let's see. We expand all this. We get that for every single element, every single combination of points in my joint probability distribution, we actually have uniform probability. Good. So we have built a joint probability distribution starting from the marginal probabilities. What we did was we multiplied the marginal probability of x times the marginal probability of y for 2 points, and that gave us the joint probability. Do you think that would work for the other example we did? Why not?
Because here, everything's the same. They're all, the probability is equal for everything.
They weren't uniform in the last one.
The one uniform in the last one, okay. And what determines if that works? What determines if the combination of my x and my y variables would equal my joint probability, of x and y marginal probabilities would equal my joint probability? Does it really matter if they're uniform or not? Is that really the descriptor, or is there anything else that can determine if that would work or not work? So notice that what we're saying here is that if we just combine our marginal probabilities, and remember, marginal probabilities treat each variable independently, right, without caring for the other. So we're saying we just take those two combinations, those two measurements that don't care about the other variable, and we combine them, we get the combined probability. So what is this implying about my two variables? If one does the other, what does this imply?
They're independent.
Exactly, right? They're independent. That's correct. So this would actually only work if my two variables are independent, which means that one will not affect the other. Because in the previous example, we don't have that, right? Our variables are not independent. We can see the probabilities actually change depending on which variable is landed on. And therefore, we can actually follow this procedure. So what we're going to talk about now, and hopefully until the end of the class, is on independence between two random variables. We've already talked a little bit about independence before, when we talked about whether two events are independent. Now we're just going to apply that into our study of probability and probability distributions. So two variables, x and y, are independent they're independent if one of these properties is true. Any one of these properties is true. First, we say that our variables are independent if, well, we already figured out that we know that if the joint probability distribution of the two variables is equal to the product of their marginal probabilities, then they're independent. And that's the example we just did, right? We found that the joint probability for flipping a coin, rolling a die was equal to the combination of the marginal probabilities. But what that means is that they are independent. There are other conditions for independence. They can be independent if the conditional probability equals the marginal probability of that same variable. So what is the second statement telling me? Well, it just says that the probability of y, given that some event x has happened, is actually the same as the probability of y regardless of the event of x.
It's basically just saying that x doesn't matter.
X doesn't matter, exactly, which means that they are independent. Okay. I have a question, thinking of this. If y is independent of x, does that mean x is independent of y?
Not always.
We'll see. So let's write this down a different way. We can also say that two variables could be independent if the opposite occurs, the converse. So I do know that at least if one of those is true, right, my variable is independent. I don't know if one is true, the other one has to be true. What we will find is that for independent variables, if one of these properties is true, all of these properties are true, which means that if y is independent of x, then x has to be independent of y. And this may not seem too intuitive, but let's think of independence not as cause and effect. Because I know that sometimes we think of dependence as, correlation, basically. We think of dependence as causation instead of correlation. But we think cause and effect. Like my grade, right, depends on my study habits. But do my study habits depend on my grade, right? You kind of think of it that way. Well, no, I have to study first, then I get my grade. But that's actually not how this works, right? We're not thinking of what causes what. We're just thinking about whether they are related or not.
Two different things.
Exactly. Those are two different things. So if y is independent of x, then x has to be independent of y, okay? Because it's not about causation, it's about correlation. It's about how they are related to each other, not about which one came first, okay? Finally, the other property is that the probability that x is contained within some region A and y is contained within some region B is equal to the product of the probability that x is contained within A and the probability that y is contained in B, which is actually just a restatement of the first statement, but with two-dimensional variables. That's all it is. If any of these properties are true, then every property in this list is true as well, which means that you only need to confirm one of these to know if two variables are independent. I want you to keep that in mind because I think that will help you for the next part of your project. If any of these is true, then they are all true. So all you need to do is confirm one of these to know whether or not it's independent or not independent. If you try the first one and it turns out that this is equal to this, then yes, they're independent. Turns out that this is not equal to this, then no, they're not independent. And none of these will be true. Okay? Independence, what it tells me is that one variable will not be affected by the other. Again, it's not about causation. And we're going to discuss causation at the very end of the class, but it's not really about that now. It's about relationship. One consequence of these properties is that we will see that if two variables are independent, then the mean of the two variables, the product of the two variables, is actually going to be equal to the product of the means of those variables. That's another nice little thing. Independent random variables will exhibit that property. I wouldn't really use this as a way to determine if two variables are independent. I would still focus on these four to determine if they're independent. This is a result of that independence, but these are prescriptors of that independence. Okay. So we can tell that two variables are independent, but I guess we also want to know, okay, if they are dependent, kind of like the degree of the relationship they have to each other. I think that would be something we can try to calculate, right? The degree of the relationship of two variables to each other. Because you may think of it, you may realize two things that are related, they could be very, very related. They could be not that much related. Can you give me some examples of different varying degrees of relationship between two variables or two things? For example, yeah, your study habits can be very related to your grade, right?
But who's in office doesn't really affect who wins the Super Bowl.
Exactly. Going back to the study example, perhaps your sister's schedule, work schedule, is also related to your grade. Because if when your sister works, she needs to use the car, you cannot take the car to the library to study. Maybe not as related as your study habits, but still somehow related. So even though we have two different things, they are related, but with different degrees of relationship, right? Your ability to have access to a laptop is related to your ability to complete today's in-class problem, right? I don't know, the shoes you're wearing may or may not be related to your ability to complete this in-class problem. Maybe you're wearing shoes that belong to someone else, and that person comes in and asks for their shoes back, and then they fight, and you move on. Who knows? The point is that even though things are related, there's different levels, there's different degrees of relationship. Okay? Which means that it will be very helpful in statistics to try to find a way to quantify that relationship. Now, I want to start off with a bit of a warning. The way we're going to quantify them is with obviously numbers, numerically. But we've got to be very, very careful not to draw conclusions from these numbers. These numbers are, I think David Spiegelhalter in Art of Statistics explains that as these numbers are guides to help us see patterns, but they're not really there to help us draw conclusions. In other words, we need to actually, our study of two variables has to go beyond just quantifying their independence or dependence. So these numbers are going to tell us whether something's very related or not related, but whether we draw conclusions over what causes what, that's a completely different thing. Okay? It's a completely different thing. I gotta keep saying this because this can touch into some interesting and maybe controversial subjects, right? When we say, well, this causes this or this that, right? I mean, you can think of a million examples on that. The first metric for quantifying the relationship between two random variables is the covariance. Now, the covariance of two random variables is, like I said, a numerical measure of some relationship between them. We say that two variables are going to have positive covariance if one increases and the other one also increases. Okay? You improve your study habits, your grade improves. Positive covariance. Okay? You increase the amount of junk food you eat, your likelihood of getting diabetes also goes up. Positive covariance, right? So when one goes up, the other one goes up, it's positive covariance. Negative covariance is when the relationships are inverted, where when one increases, the other one decreases. Okay? And you can think of many examples of negative covariance. And finally, zero covariance if there isn't a clear discernible pattern between them. There's an interesting, not interesting, maybe not interesting to you, interesting to me. There's some research we're doing now. Because I'm sharing these videos, right? Because I'm recording the lectures. I kind of feel worried about actually showing you data that we haven't published that we are in the process of publishing. But the research I do in my studies is pretty much biological, like biomechanics, biology, bioengineering. And sometimes we want to see if there's any relationship between an animal's size and then some property of that animal. Just recently, we're looking at size versus the diameter of your rectum, right? Which kind of dictates the size of your turds, right? And it's pretty interesting because when we plotted that data, we didn't see visually a discernible pattern. But if we tried plotting it in log space, right, instead of a standard 1, 2, 3, 4, 5 scale, but 1, 10, 100, 1,000, we could actually see a nice little increase in pattern. So we were able to conclude that yes, as body mass increases, so does the size of the turds, up to a certain point. After a certain point, the animals get bigger, but the turds actually get smaller, which is pretty interesting. It has a lot to do with diet. For example, whales, all they eat is like little plankton and whatever, so they don't need big solid turds, they just need small little liquidy, right? But elephants, they eat nice healthy dinners, right? But whales are much bigger than elephants. So it's like, it kind of goes up until the elephant, and then
Fiber from all those branches.
Mm-hmm. So what's interesting is that we are able to tell that relationship just by looking at a graph. And obviously we're going to learn about graphing and what we call descriptive statistics. I think that's actually next week, next Wednesday. But sometimes we can't actually discern a pattern at all. There was a paper published a few years ago, maybe 5 or 6 years ago, that it pretty much says that your body mass actually doesn't determine how long you're urinating. And how the researchers found that, that's actually one of my advisor and his previous students, how they found that was by, again, looking at different data and finding that they had zero covariance. There was no pattern of increase and decrease. Does that mean that everybody urinates at exactly the same amount of time? Exactly, no. What it does mean is that you can't really predict how long a kid is going to take compared to how long an adult. It's probably going to be on average the same number, right? So covariance is pretty interesting because if we can't identify patterns, then the covariance is 0. Now, I want you to be careful here because if two variables are independent, for sure their covariance will be 0. However, sometimes we get 0 covariance, right, depending on how we calculate it. That doesn't mean that two variables are independent. That just means that we can't actually see that dependence with our tools. That's why I say these numbers, you want to be careful. They're there to guide you, but you can't really draw conclusions from them.
What if in one, like, so I was just recently watching one video, it was about money and happiness, and it was like money actually brings happiness until the middle class, like medium income. And after that, it's not really related to happiness. So what kind is that? Because at some point, so the more money you have, based on that study, you're happier. But after that, there is no like significant data to show that after a certain point it really brings you happiness anymore. So what kind is that?
So I think what you're thinking of is causation, though. So those are two different things, right? So you're thinking about whether money brings you happiness. So you're thinking, how much money do you have? What's the degree of happiness that person makes?
Income, technically.
Income, yeah. So one of the things is, first of all, we don't really care about causation right now. All we care about is the relationship. Is there a relationship? Yes or no? Now, the clear answer to yours is that yes, there is a relationship. Whether it's good or bad, or whether it changes or stays stagnant, there is some relationship. So in that case, right, and this is why it's important to understand that these are just guides. If you were to just plot for, I guess poverty all the way to upper middle class, you would notice a positive covariance. You can make some conclusions about that if you want. But then if you plot from upper middle class to, I don't know, like billionaires, you probably notice 0 covariance. Just because there's 0 covariance for this side doesn't mean that they're independent, because we already know from the previous plot that they are dependent. So that's why I think it's important to understand that this is not really about causation. And again, what part of the data you're seeing is going to affect the covariance. And that's actually really important. A really nice example, right, where you can actually look at different sides of your sample space and observe different covariances. And that's not just there, right? You can see it with anything. Like if you are measuring something, let's say you get this cloud of numbers. I really want to show you the data that I have from my research, but like I said, I want to publish it first. I want any of you becoming famous biologists with my own work. I have to do all the dirty work of measuring, right? So I don't want any of you to take credit for that. What type of covariance do you think that is? Okay, but if I were to focus on these 4 points, what type of covariance am I looking at? So really, being able to see the entire sample space is very, very important. I would love to be a sad billionaire. I'm not there yet, so I can't tell you.
So it's subjective.
Yeah. That one is interesting because degree of happiness is actually very, very subjective. Right? I'm very happy with my life right now. But I have things that, I don't have things that other people will probably need to say that they're happy. I've been wearing the same clothes for the past 6 years now. And you may think, wait a minute, that sounds kind of miserable. Look at my shoe, it has a hole. Look at my shoe, it has a hole.
Like, if you want to, I'm assuming, but the business you have a company for yourself, if you want, you can get it, you just don't want it. You know what I'm saying?
Yeah.
So that's different. You're rather than someone wants to have something and doesn't have it at all.
It's painful. So, the thing is, happiness is still very subjective. I'm extremely happy now. I'm happy that I make enough money to support myself, my wife, my cats, perhaps a kid. If we ever have kids, and I stay in my current path, I think we'll be good. But if you were to ask me how happy I am on the day when I argue with my wife, my answer is going to be very different. If you ask me how happy I am right before I'm paying taxes, I pay ridiculous amounts in taxes right now compared to last year.
I know.
And my happiness is just, that day is just like, wow, what was that? It took me like a week to actually just pay it. I was like,
Buy yourself a jet and ride it up.
yeah. I was thinking, what else? It's already 2021, so I can't do it. It's like, I was in that, we all go through that spot where we're like, should we? No, that's wrong. And then we just do the right thing. But I was there for about a week. So it's very, I would say it's very subjective. I do have friends that are much, much higher income than I am, and they do say that after they pretty much reached about $1 million in net income per year, then for them life is pretty much the same. It's just like a hustle, just to get more and not lose what you have. And I kind of get that. Right now I'm kind of in that path where I just try to keep going higher and higher and higher. And that's why I work a lot, that's why I neglect my physical health, which is not something I should do, right? But that's why I do it, because for me, that's the measure of my happiness. But it's very subjective, like I said. It's really, really, really subjective. We're going to get to that on the last day of classes. I'm trying to prepare. I know I said we're going to talk about the final exam, and I will do that, but I also try to prepare about an hour and a half of kind of like more real statistical examples. So I've been reading some books and putting together examples. And one of the things we want to talk about is called the wisdom of the crowds. It's not just about what I think personally, but perhaps that we can get what a lot of people think, that perhaps we can find a good level. But for now, let's not think of causation. For now, let's not think this causes this. Let's just say whether this is related to that. Okay? But very, very good point, Rantim. I'm going to show you some examples, and these are actually from your book, which I put right here. Let me show this sheet here. Okay, so this is actually from your book. I forget the figure number, but it's there somewhere. And these are 4 examples of different random variables and their covariance. The positive covariance is something that we can clearly identify, right? Positive covariance, we have this really, really nice positive trend, upward trend. Notice that you have to actually look at the data as a whole to notice that positive covariance, because if you look at individual points, for example, if I were to focus only on this blob of points, I cannot really tell the covariance. Negative covariance, again, very, very easy to note, but you need to look at your data as a whole. And zero covariance is when you can't actually discern a pattern. You can't really tell whether one increases as the other increases, as you can see in the examples here. Looking at the data as a whole is just really, really, really important, right? Because it will allow you to look at trends. One thing I'm really into, I really like church history, Christian church history. I like theology. and I like in general statistics about religion. And one of the things we always talk about it at church. It's like, oh no, it's like church attendance is dwindling, right? Especially in America, church attendance, pretty much in any country that's Christian majority, church attendance decreases. It's decreasing. And if you actually look at the number of self-professed Christians in any, I guess, first world country, that number is actually decreasing. And you may say, oh no, Christianity is in danger, all that stuff. If you look at the number of Christians as a whole for the world, that number is increasing, right? So it's pretty interesting because, you got to look at the entire thing to actually be able to draw conclusions. So number of Christians as a whole in the world increasing, number of Christians in first world countries decreasing. So obviously there has to be something making up for the other. Same thing with Islam, adherence to Islam in first world countries increasing, right? And then adherence to Islam in what's Islamist countries is actually remaining pretty much the same.
Well, actually, it's decreasing. At the same time, I can talk about my own country.
Okay.
The mosques are empty.
Oh, really?
It's empty, absolutely.
Okay.
And here I have friends that just convert to Islam and they try to preach me. I'm like,
Dude.
I'm already at the
Look at me.
I'm already at the end of the path that you're starting. So I think that's the reason that
Yeah.
people who just convert, they're just more into doing it in any religion, and then people who are like, let's say, Christian already in America for the past 30 years, they already seen what is the end of it, being a bad experience or anything that can be.
Yeah. So we can draw completely different conclusions depending on what data we're looking for. And that's why it's very important to have a really, really broad view, right? Try not to, I know that you always want to focus on what it is you want to study, but it is very important to have a broad view in order to identify correlations properly. Sometimes it's impossible. Like, I can't actually survey every Christian and every Muslim in the world and say, hey, are you Christian? Hey, are you Muslim? Hey, are you something else? I can't. But I need to at least focus on sample spaces that actually are representative of a population. And I know we talked about this earlier in class. I think it was nice to bring, to go back to this just a little bit. So, yeah, these are some examples of covariance. There's another example. This I got it from the internet. I know nothing of cars, so don't make me try to explain it. But essentially, it's like car mass versus car efficiency. Are smaller cars more efficient? If you look at this graph and I say, I would like, and when I say efficiency, it's like mileage per gallon. So if I say I would like a very, very environmentally friendly car with, I want to be able to drive as I can with as least gasoline as I can. Should I get a lighter car or a heavier car?
AKA a boring car. You should get a lighter car.
So that's true. However, you can see that it's not as clear, right? We have definitely those trend lines to kind of like guide us to show us where the trends are going, and we'll learn how to build those trend lines in a future class. But the idea is, I need to look at things as a whole, right? I can't just look at individual cars to draw my conclusion, because if you look at individual cars, it's all over the place. You could even selectively, right, choose some data points that are going to show positive covariance, and then just display that and sell it to whoever you want to sell it to, right? So that's essentially what covariance is. But I've talked a little bit about the concept. I haven't really talked about how we actually calculate it. So let me just show you a little bit of the calculation of covariance. Covariance, as the name more or less implies, is related to the variance. And we say that the covariance of two variables, so sigma of x and y, sometimes we write it down as the covariance function, so covariance of x and y, is equal to the mean of x times y, so the mean of the product of variables, minus the product of the means of the individual variables. You can see from this equation that if the two variables are independent, my covariance has to be 0, because if the two variables are independent, then this and this are the same thing. However, just because it's 0 doesn't necessarily mean independence. So keep that in mind. Just because it's 0 does not necessarily mean independence. Okay? So that is my covariance. There is another measure that we are going to solve for, and that is the correlation. Okay. The correlation between two random variables is simply a scale of the covariance of those variables. So essentially, we're taking the covariance and then we're just scaling it so that we can, for example, we can compare, for example, apples to oranges. We have covariance, we get covariance of 2, covariance of 5, but what does that mean, right? It doesn't really mean anything unless we actually find some way to relate them. So the correlation does that. The correlation just takes the covariance and then just scales it into a scale that goes from -1 to 1. So we can say -1, the most negative covariance, and 1, the most positive covariance, and then everything in between. So my correlation is a scale between -1 and 1. And I misspoke. The closer to those limits, so the closer to -1 and 1, then the more negative and positive covariance respectively. Oh no, I didn't misspeak. It's the same. If two variables are independent, then the correlation would also be 0. So basically, from independent you go to 0, and then from positive covariance you go all the way to 1, and negative covariance all the way to -1, and then everything in between. The correlation, which is rho of xy, is going to be equal to the covariance divided by the standard deviations of each individual variable. What this means is that if the covariance is equal to the product of the standard deviations of the individual variables, then the correlation is 1 or -1, depending upon its negative. And that kind of gives us like total correlation, right? The most quantifiable or observable relationship between the two. That's 413. I'd like to give you about 15 minutes to do a problem, for you to solve a problem, okay? We already, and you can work in pairs if you want, but when you submit it, you need to write down who you worked with, okay? Hang on, does everybody here have a laptop?
Mine just died. So I'm moving on.
Okay, you can work with someone. So yeah, work in pairs and write down who you worked with. If you don't want to work in pairs, you can work individually, it's fine, you'll have time. So we did this example with signal strength and response time. And we already solved the marginal probabilities in the class. I would like to know, I would like for you to tell me the measures for each individual variable. And when I say measures, really what I mean are the mean, variance, and standard deviation for each variable, for x and y. And then I would like you to tell me how these two variables are related. In other words, I'm asking for the covariance and the correlation. You have all the equations you need. It's just a matter of being able to identify what you need to plug into each equation. So give me the mean, give me the variance, give me the standard deviation, give me the covariance, give me the correlation, and at the end, I'd like for you to answer the question, are these two variables independent? Okay? You'll have 15 minutes to work through that, and then we'll go over the result after you submit it.
So I got this example. That has, main variance and
When you have solved it, you can go to D2O on the assignments tab. If you scroll down to the assignments for today, one of them is called in-class problem 1. That's where I want you to upload. You can upload an Excel spreadsheet if you want. You can upload a Word document, PDF, whatever you want, as long as your results are there.